Okay. And then here's some object. I'm moving it 3 feet from 0, 0 to 3, 0. So this is how the object is moving. So by giving you that part, what am I giving you in the work formula? The distance. Good. So the distance is 3. Now I give you the vector, and we're going to have to use something that we've done over the last couple days to find theta. So I have a vector of 1, 2, which is, so that's the angle that the force is pulling, so this is theta. So I do have to find theta, right? So because I have the distance is 3 feet, I have the force, 10 pounds. Essentially what I'm doing with that cosine of theta is I'm figuring out how much of that 10-pound force is acting in that same direction. Okay. All right, so what are your ideas of how to find theta? Think back to what we did yesterday or the day before. If we would have 2 vectors, I would need to find I could do that, but there was an easier one if I just wanted to find theta, the direction angle of a vector. What could I use? Something inverse?
Cosine inverse v1 over magnitude.
Yep, or you could use tan inverse of?
v2 over.
Yep, either of those things. I'm going to do tan inverse, just because I see that it's in quadrant 1 and I have 2 and 1. Okay, so I'm going to do that. What do we get?
Wait, is it tan or tan inverse?
Oh, crapola. Tan inverse. Thank you. Thanks, Bobby. Always keeping me on my toes. Good. 63.4-ish. Okay. Just to be a little more accurate, I'll add a decimal. It's not a big deal if you don't. Okay. Because I'm going to use it in another equation. So, or you could even store it if you wanted. Like, just leave it in your calculator if you wanted to be most exact. So here we go. Work equals force. What am I going to put for force? 10 times cosine of 63.4 times the distance, which is 3. Oh, okay. And so we do that, and we should get 13.4, and the measurement of work, this might seem odd to you, is foot-pounds. Because you're taking your 2 different things and putting them together. 1 foot-pound would be the amount of work required to move 1 pound, 1 foot. That's what a foot-pound is. Okay. Alrighty. Now, what if I don't have you moving it along the x-axis? Let's look at example 2. So, number 2, remember what I said, theta is the angle between the vector and the line of movement. We could use tan inverse because it formed a right triangle. Find the work done by a force of 30 pounds. We have force of 30 pounds. We have that. And I'm gonna give you the distance, even though I didn't say I was. But find the work done by a force of 30 pounds, acting in the direction 2, 2, to a point in the first quadrant along the line y equals 0.5x. And I'm gonna write. We're gonna do the same thing, moving an object 3 feet again. Okay. So this would be like maybe I have an object moving up a ramp or something like that, okay? And the line 0.5x just has a slope of 0.5 or 1/2. So let's just think about that. If something has a slope of 1/2, rise over run. Yep, rise over run, 1 over 2. That means it's going up 1 over 2. Okay, so I'm going to graph that line. So up 1 over 2. Up 1 over 2. Left. Right. Holy cat. And the slope of the line, this is related to tangent. The slope of the line, think of rise over run. The slope of the line is like the tangent of the triangle formed, okay? Because it's 1, that's like its opposite piece, over 2. So this is a direction of 2, 1. Okay, now, this is my object. Let's say it's a little box, okay? And I'm trying to move that box 3 feet up that line. The vector that's acting on the box has a direction of 2, 2. So here's my vector 2, 2. Okay. So now theta is this angle right here. Well, shoot. Can't use just the tan inverse of 2 over 2, because what would that give me? This whole angle. Oh! Subtraction. Yes! What if I found, I'm going to do some color coding here, because it's fun. Alright, so what if I found this whole angle? I'll call that theta 1. What other color should I use? Pink. Alright. I know it is. I'm going to call this angle theta 2, because both of those are right triangles. And then how would I find theta from those? Just subtract the big angle minus the small angle. Okay. Alright, so we're going to split you into 2 groups. Rows 1, 2, and 3. Would you guys find theta 1 for me? So you're using 2 over 2. Maybe you know what it is already. Would you 3 rows find theta 2? You're using tan inverse of 1/2, because 1/2 is the rise over the run or the opposite over adjacent. Okay? Do you understand why I said you might not need a calculator for the first one? Because if you're going up, yeah, 2, 2, 3, 3, 4, 4, that's halfway through that quadrant, right? Now you can use tan inverse if you want, but what did you guys get? That angle with 2, 2 makes with the ground is 45. How about you folks over here? 26.6? Okay. Alright, guys, would you subtract those 2 things, theta 1 minus theta 2, to give us theta 18.4? If I used this rounding. Okay. Alright, here we go. Now we know the angle made between the vector pulling the object and the line that the object is going. By the way, you only have to do this if it's a line other than the horizontal. Okay? So we go back to the work formula. Work equals force. What was the force? 30 pounds times the cosine of the angle made between the vector and the object. So that's 18.4. And I told you the distance was 3. Really? I got a really lot bigger than that. Are you in the right mode? right, so 85.4, does that sound about right when you type in? Okay, cool. For work, if the force is given in pounds and you're moving it in feet, it would be foot-pounds. Everything we would do would be. If there's other units, then you would have, you could have like foot inches, or foot-pounds, no. Foot, what's another force? Something with kilograms, I guess, right?
You know what, I don't like how America's the only country that doesn't use the metric system. It's so annoying. The metric system is the country is so small and thin.
Because we all need to do the metric.
Oh my god.
All right, let's take a look at example 3. Example 3 has to do with also this idea of forces, but just kind of breaking down the components of vectors, okay? So Becky is sitting on a sled Becky is sitting on a sled on the side of a hill inclined at 30 degrees. Okay. That's probably a little bigger than 30 degrees, but oh well. All right. So the combined weight of Becky and the sled is 130 pounds. Okay. Little Becky. Okay. Oh boy, so I'm going to have to draw Becky here. Here's Becky's sled. She's standing on the sled. All right, this is about all the drawing you're going to get from me. All right, so the question is, what force is required to keep the sled from sledding down the hill? Okay, so I'm going to try to draw a little triangle here. By the way, what's this angle? Okay, so here's what I'm going to do, guys. I'm going to draw a triangle such that this leg is perpendicular with the hill. Okay. It's another little right triangle. Okay? The combined weight of Becky and the sled is going to be this piece, because we'll assume wherever this is, let's say it's the top of the hill, but wherever the sled is weighing straight down, and that force is 130 pounds. So, can you identify then in this triangle? I'm trying to figure out what force is required to keep the sled from sliding down. Where do you think that would be? Just thinking logically. Yeah, so right here, the force that is required to keep it there, okay? And so we're going to, because these are forces, this is a force pulling it down, okay? I'm trying to find this piece, this force right here. So I'm going to write F represents the force that's holding that sled up. Using trigonometry, meaning SOHCAHTOA, how could I find that force with the given information? And again, you could find other angles if you wanted. Do you understand how I got the 60 because this was 30? Okay. And then I made, okay, a right triangle from that by extending a perpendicular from the hill. So this is 60. What piece is this? Adjacent. What piece is this? Hypotenuse. So let's set something up here. Which one uses adjacent? Okay. So I'm going to write the cosine of 60 degrees equals adjacent, which I do not know, but I'm going to find the force, over the hypotenuse, which is 130. All right, can you guys find that for me, please? Did you get 65 pounds? Okay. Now I hope that makes sense, because part of this 130 is going this way, there's partly part of that 130 pounds that's working for her because it's holding her kind of still up there, but then another force would have to act not as much to keep the sled up, so 65 pounds. Does that make sense? Okay. All right, cool.